Of you all know Hamerly? How many of you all own Hamerly? Farm Hamerly? I see a few nods, but not too many nods. So the point that I'm getting at here is, you know, here's 4 Hamerly profiles. You can't see this. Can I walk around without tripping? You can't see this very well, but these are 4 Hamerly soil profiles that are taken where they've done this detailed chemical work, and what we're looking at here is salinity with depth. Now this was the saline phase Hamerly. Electrical conductivity is basically 16. Okay, that's a third of, well, not quite. Yeah, it is. It's a third of the seawater. So we're not interested in that. It's horrible. But look at the other 3 normal Hamerlys, and look at the range in salinity in that. We see the same sort of thing in the nature of certain types of ions that are held on the clay exchange complex, and those values can change with depth. And if they change with depth, then they have an effect on the physical structure of soil. And I've got a picture here that I'd like to show that shows a bacteria. John, you got a stopwatch? This is a bacterium right here. This is pretty small. These are all tiny little aggregates of clay, and you can see that they're kind of flat, right? You can see a pattern in there, right? They believe me, they really do. Okay. Anyway, this aggregation is caused by the organic fraction and by specific cations like calcium and magnesium that allow these clays to be pulled together. Okay? And you want clays to be pulled together. You all, if you were in fact in a situation that we refer to as flocculated, this is mostly men, every person in here would be within the tent. You'd be close together if you were flocculated. And that would be a good thing, because then there'd be porosity and aeration around you and water could flow. When the wrong kind of specific cations are on the exchange complex, you all picture right now if you could put a hula hoop around you and have it strong. This guy puts a hula hoop around and he makes it strong, and all of a sudden this guy's bouncing, and you're bouncing. You bounce right off the pole. This is the idea of some of the sodium-affected soils that exist in the valley and regionally. If your clays at depth in the soil, if they've got a significant component of sodium on them, that sodium can affect the structure, which affects the flow rates. And the only way that you're going to know that kind of thing is to look at this characterization data that we have. And what I'm really trying to push today is the idea that for some of you, you really need to look at those soils and try to determine whether or not you've got a little bit of soil testing and go a long way to ensure long-term viability of the tile drain system. Because if we have, as we drop the salt content, that's why you're doing it, right? You're dropping it for temperature, salt content, many reasons. As you drop that salt content with depth, there's physical chemical processes that go on with those clays, and they can get dispersed. They can get dispersed, and then the porosity and the hydraulic conductivity are significantly changed as a result of that. That's a serious problem. It's nothing that's going to take place in 1 month. It's going to play out over a period of time, and it's something that we need to pay attention to. For 7% of you, for 9% of you. Okay? I mean, tiling is doing great things in the valley. There's no question about it. But you don't want to be part of that 7% or that 5% that might be putting tile in on soils that have high sodium levels at depth and salts, and then as you reduce the salt load, what happens is the sodium can now start bearing its influence, and that's the hula hoop idea of the clays repelling each other. You all want your clays to be, they're negatively charged, that's what holds on to your nutrients. You want those clays to be what we call flocculated.